So, we have been discussing the resistance concepts. We are going to take a specific case in today's lecture. It is called the re-radiating surface. Okay. So, re-radiating surface is essentially the one where no heat is lost or given lost from or given to. So, no heat is lost from or given to that surface, and that is what is called as a re-radiating surface. In some sense it is like an adiabatic surface. Okay. So, suppose I have a suppose surface 1 is the re-radiating surface, which is basically adiabatic, and if I have surface 2 and surface 3 and I specify the temperatures T1, T2, T3, A1, A2 and A3, and the emissivity is epsilon 1, epsilon 2 and epsilon 3. So, now I can write the resistances for this problem and find out what is the net heat exchange between 1 and 2. So, note that there is nothing that is leaving surface 1. So, there is no heat that is lost from surface 1 and nothing is added to surface 1. So, keep in mind that the resistance of every surface is not to its atmosphere, it is actually to its corresponding black body. So, note that the driving force is the difference in the black body radiation and the emission from that surface. So, there are totally 6 resistances. There are totally 6 resistances. So, this is EB1, except that the Q2, the amount of heat that is given or taken out from that surface is 0. So, nothing comes here and nothing goes out. Okay. And so, this will be 1 minus epsilon 1 by A1 epsilon 1, that is the resistance here, and this is EB3 1 minus epsilon 3 by A3 epsilon 3, and this is EB2 1 minus epsilon 2 by A2 epsilon 2, and this will be 1 by A1 F1 F12 will be 1 by A1 F13 will be 1 by A2 F23. So, that is the resistances. So, we have 6 resistances, 3 resistances for exchange between each of these 3 surfaces, and 3 resistances for the driving force for the amount of heat that is absorbed or the net amount of heat that is absorbed or liberated by that surface. Q3 is the amount of heat that is supplied to surface 3. So, what is the total resistance? What is the total resistance? It will be 1 minus epsilon 3 by A3 epsilon 3 plus, so of course you will have this one 1 minus epsilon 2 by A2 epsilon 2. What is the resistance for this component J1 J2? So, that is parallel. So, it will be 1 by A F23 plus 1 by, so that will be 1 by A1 F13 plus 1 by A1 F12 inverse of that. So, that will be the total resistance. Essentially, these two resistances are in parallel with this resistance which is present here, okay. And because there is no heat that is coming out or going out or coming in from here, this resistance does not play any role in the total radiation calculation, although it does not mean that the resistance is negligible, it's just that it does not play any role in the calculations, that is all, okay. So, that is the total resistance, and now you should be able to calculate the radiation exchange, overall radiation exchange, etc. Suppose you have radiation and convection and conduction simultaneously, okay. So, suppose you have all three processes occurring simultaneously. We have not dealt with convection in detail, but let us say assume that you know how to work around with convection properties. So, if all three heat transfer modes are occurring simultaneously, okay, through a surface, then it is essentially all modes are in parallel. So, that is the first thing, okay, because these are independent modes of heat transfer. So, supposing you have one surface, this is surface 1 and you have surface 2, okay. Now, let us say that there is radiation mode of heat exchange between 1 and 2, okay. Now, in principle, if there is a media in between, we are going to see in a short while how to characterize radiation in this medium, but let us assume that there is no radiation, which means that if the medium is transparent, if the media is transparent to radiation, which means there is no absorption or emission, whatever is coming in this side is transmitted to the other side of the medium, and there are media which actually has this property, and we will see that in a short while. But there could be conduction through this media, right. There could be conduction mode of heat transport from surface 1 to 2, and if the media is flowing with a certain velocity, there could always be a convective mode of heat transport from surface 1 to 2. So, the way to characterize this is, supposing if this is surface 1 and the amount of heat that is provided to surface 1 is Q, then it is just that all three are happening in parallel. So, if you are able to find out the driving force and resistances for each of these mode of transport, then we could represent it as resistance for conduction, resistance for convection and resistance for radiation. Okay. So, if we know how to find the driving force, and most of the cases we know, for conduction we know that temperature difference is the driving force, for radiation we know that the exchange between the two surfaces is the driving force for radiation exchange, and for convection also it is the temperature difference which is the driving force. So, if we know that, then we can find the resistances, and we should be able to incorporate the multiple mode of heat transport in a very easy fashion if you know how to construct the resistance network. So, note that this is true only when there is constant rate of heat transport in the media. If there is heat generation, obviously you cannot write resistance networks for conduction mode of heat transport. In that case, you will have to write the full model and solve the full problem. Okay. So, we will actually deal with coupling of convection and conduction when we actually look at heat exchangers. Let us assume that we know how to characterize convection, and this is the way to include all three modes of heat transport, and I want to include this for sake of completeness of radiation processes. Okay. So, we are going to see volumetric absorption. So, when we initiated discussion on radiation, so we observed that the radiation is a surface area process for solids and liquids which is present in a certain container, but for gases it is a volumetric process. So, if we suppose we assume that we have two surfaces, okay, surface 1 and surface 2, and let us say it is filled with some gas, okay. So, the aspect of volumetric absorption depends upon the nature of the gas. So, supposing if it is a non-polar gas, okay, it is a non-polar gas, for example like oxygen, okay, it is a non-polar gas, they have almost no radiation absorption, the absorptivity is almost 0. They do not absorb or emit radiation, and that is because of the nature of the gas. It is a non-polar gas, and so they do not absorb or emit radiation. But supposing if I have polar gases, what is a good example of a polar gas? Ammonia, okay. So, ammonia is polar, carbon dioxide is polar, and you have water vapor is polar, it is a gaseous state, they are all polar gases. So, they have the ability to absorb and emit radiation at different locations in the medium, okay. So, when I say these non-polar gases do not absorb or emit, they are essentially transparent to radiation. Which means that the transmittivity is equal to 1, okay. But for polar gases that is not necessarily the case. The other properties of polar gases is that the reflectivity is almost negligible. So, these are properties, okay. So, they have negligible reflection. So, they just emit, absorb and transmit, okay. So, the volumetric absorption process, they occur typically in what is called the wavelength bands. So, they observe in wavelength band. So, it is not like a specific wavelength at which the emission and absorption is going to occur, it is going to be a band in which they are going to absorb and emit radiation, okay. So, what we are going to see for the next 15 minutes or so is to find out how to characterize this process. So, in order to characterize, we need to define, so not that we want to characterize this process of absorption of radiation. So, there has to be some intrinsic property which quantifies the absorption process, right. So, that is what is called the absorption coefficient. So, it is like when you had conductivity which quantifies the amount of heat that it conducts, or rho Cp which is the intrinsic property to store heat in a system. So, similarly absorption coefficient is the quantity which quantifies the amount of radiation that is absorbed by a given medium. So, it is represented as kappa, and of course, it is a function of the wavelength, and the units are per meter. So, it basically tells you what is the quantity of radiation that is absorbed as you go into the media per unit length, okay. So, as you go, how much is absorbed, that is what is quantified by absorption coefficient, okay. So suppose I have a gas which is filled inside these two plates, surface 1, surface 2, and let us say the intensity of radiation that enters the gas at surface 1 is I lambda naught, okay. And if the width of separation is 0 to L, okay. So width of separation is 0 to L, and if I call this as my x coordinate system. So now we said that it is occurring in wavelength band, and therefore we can write a differential balance. So if this thickness is delta x, okay, and if the intensity of radiation that occurs at some x location is I lambda x, and what leaves is I lambda x plus dx, okay. So that is the flux of intensity that leaves, and if the cross sectional area of radiation outside the board, so this is perpendicular to the board, so if the cross sectional area is A, the cross sectional area is A, so now I can write a energy balance for this system. So if it is a steady state process, assume steady state, then whatever enters this element here should be equal to what leaves the element plus whatever is absorbed, okay. So that will be A times I lambda x, that is the net rate at which the radiation is entering that element, that should be equal to area into I lambda x plus dx plus whatever is absorbed. Now note that this is I should have mentioned this, absorption coefficient is actually the fraction of radiation that is absorbed at that location, right. So that will be k lambda into A I lambda x multiplied by dx, okay. So that will be the net radiation, the total amount of radiation that is absorbed. So this is the radiation absorbed by the gas in dx, okay. So that is the amount of radiation that is absorbed. So after simple algebra, so you will see that we can rewrite this as d I lambda x by dx equal to minus kappa lambda, okay. I can solve this equation, I lambda x equal to some constant into exponential of minus kappa lambda into x. How do we find this constant? So remember the picture, what is entering is surface 1, surface 2, what is entering at x equal to 0 is I lambda naught, okay. So if I know how to measure that, I am done, right. So at x equal to 0, that is the boundary condition. Okay. So I can substitute that and I can find out that I lambda divided by equal to exponential of minus k lambda x, okay. So what will be the intensity with which the radiation leaves the surface at L? What will be the intensity with which the radiation will hit surface 2? Is I lambda L, right. So I substitute this. So radiation received by surface 2 is I lambda L by minus does this expression look familiar? Beer-Lambert law, right. So, this is what is called as Beer-Lambert's law.